Now we are going to take our third and final look at improper integrals. We are going to look at what I call type 3 improper integrals, which is going to be different than types 1 and 2 that we saw in the previous two videos. However, if you haven't seen those yet, you might want to watch them first. Now what we are going to look at is functions over bounded domains, and yet the integral is still going to be improper. So let me explain how that can happen. Suppose we have a function and we are trying to compute its definite integral from a to b, where notice that both of these bounds are finite. So we're no longer looking at a domain that goes off to infinity or negative infinity in either direction. However, suppose the function has, say, a vertical asymptote somewhere in its domain. In particular, on this slide, we are describing the situation where it might have a vertical asymptote at the right side of the domain or at the left side of the domain. Then you still might enclose an infinite amount of area between the x-axis and the graph of the function. So for example, for this first scenario, suppose we have the domain going from a to b. So it's a nice bounded domain. That's what we like to see with Riemann integration, but perhaps the function approaches plus or minus infinity as it approaches b from the left. So maybe we have a function that's pretty nice, and then it grows to infinity as it approaches some vertical asymptote. Even though the domain is finite, it's still possible that because of the behavior as we squeeze area between the graph of our function and this vertical asymptote at x equals b, we still might be looking at an infinite amount of area here, in which case our improper integral of this type would diverge. If, however, the area that we enclose here is not too much, in fact, this improper integral will exist and equal a number, then we'll say that it converges. So what we're going to look at first is examples where the asymptote occurs at either x or b. So in this picture, it's occurring at b, but it could also occur at the left side of the domain. And then we will also say, it could happen in the middle of the domain, in which case we just break the computation up into two pieces. The strategy for evaluating these improper integrals is going to be like what we did in the previous two videos. We are going to take the problematic bound. In this case, it's b. So for this picture, we are approaching infinity for this function as x approaches b from the left. We will replace that with a number called t, and then we will let t approach b. So rather than approaching infinity, t here is going to approach the place where we have a vertical asymptote. So let's go ahead and look at some examples. Let's see if we can compute the integral from 0 to 2 of the function y equals x over the square root of 4 minus x squared. Notice here that as x approaches 2 from the left, the square root of 4 minus x squared is approaching 0, because this is going to look like square root of 4 minus 4. So therefore, x over the square root of 4 minus x squared, this is approaching positive infinity. So we're looking at a vertical asymptote where the function is growing to infinity as we approach 2 from the left. What we are going to do with improper integrals in this situation is we're going to say, let's truncate our domain so that we don't get all the way to 2. In particular, let me switch markers. Let's instead evaluate from 0 to t, where for any particular value of t, t is just to the left of 2. Then we will do this definite integral for x over 4 minus x squared. For any value t to the left of 2, the area is finite, and this definite integral will exist. But does the area trend anywhere? So in particular, what happens if we let t get closer and closer and closer to 2? So we'll say, what is the limit as t approaches 2 from the left of this integral from 0 to t of the original function? This is a u sub situation. Let's set u to be 4 minus x squared, so that du is negative 2x dx. I'll write negative 1/2 du is x dx. That will take care of the numerator. We will change our bounds, and they will change in terms of t. So we saw examples like this in the previous lectures on improper integrals. We will have the limit as t approaches 2 from the left of, I'll change my bounds last, 1 over the square root of u is u to the negative 1/2, and then x dx is negative 1/2 du. So that's our new integrand. When x is 0 for the lower bound, u is 4 minus 0 squared. So the lower bound for this is 4. On the other hand, when x is t, so if we look at the upper bound, u is 4 minus t squared. So we'll put that in. Okay, now we can anti-differentiate in the usual way, leaving the limiting process in front. So this is the limit as t goes to 2 from the left of, let's see, this antiderivative is u to the 1/2, but I'm not done yet. If 1/2 dropped down, I would need a negative here. Okay, so that's going to be the antiderivative for this integrand. But we have a definite integral here where the bounds are 4 and the top bound is 4 minus t squared, like that. Now we need to plug in those bounds, and I'm going to take u to the 1/2 and revert back to a square root symbol. So this is going to be the limit as t approaches 2 from the left of negative square root 4 minus t squared. That's what I get when I plug in the top bound. Minus negative, so plus square root of 4, which is 2. Okay, let's take a look at this. When t approaches 2 from the left, as we approach 2 from the left, this square root is always defined, and it's approaching the square root of 4 minus 4. So overall, this first term is going to be 0. This one is 2. So we conclude that this limit exists and equals 2. So our original improper integral converges. So even though this function has a vertical asymptote at x equals 2, it's still enclosing a finite amount of area under the curve. In fact, this improper integral exists and tells us that that area is 2. Now we are going to work through a two-part example, which is going to be similar to a two-part example that we did in the improper integrals type 1 video. In this context, we are looking to evaluate 1 over x from 0 to 1. Notice that there's an asymptote at x equals 0, because as we approach 0 from the left, this function grows to infinity. So what we're going to need to do is take this integral as it's written and switch it to the limit as t approaches 0 from the right. So that's the direction we want to approach this lower bound. So we'll take the limit of the definite integral from t to 1 of 1 over x dx. You might anticipate, if you remember the examples that we did in part 1, that in a minute we are going to look at 1 over x to the p. We have to do this case first, separately, the case when p equals 1, because the antiderivative of this expression is natural log, and that's kind of a special situation. So if I go ahead now and evaluate this, we'll have the limit as t approaches 0 from the right of natural log of x. X here is positive, so I'm going to omit absolute values. And the bounds go from t to 1. Plug these in, let's see what we get. The limit as t approaches 0 from the right of natural log of 1 minus natural log of t. Okay, it's always nice to review natural log for a moment. So natural log of 1 is 0. But as we approach 0 from the right, natural log travels down to negative infinity. So it has an asymptote at x equals 0. This expression, just this part without the minus, is going to negative infinity, so that overall, this computation is going to positive infinity. So this limit does not exist and equal a finite number. Therefore, this improper integral diverges. So this will be the situation when the power on the denominator is 1. In other words, we're looking at 1 over x to the 1. Now let's look at the same setup, but for 1 over x to the p. We're ready to look at the improper integral from 0 to 1 of 1 over x to the p dx, where p here is not equal to 1 because we just did that one. So let's get going. We will say the beginning is going to be the same. So let's take the limit as t goes to 0 from the right of the definite integral from t to 1 of x to the negative p dx. Because we're not looking at the special situation of 1 over x having an antiderivative that looks like natural log, we can just use power rule here to say that this is the limit as t goes to 0 from the right of x to the 1 minus p times 1 over 1 minus p. And then we need to plug in our bounds of t and 1. Let me expand this, and then I'll give you a minute to see if you can reach the conclusion on your own. This is going to be the limit as t approaches 0 from the right of, let's see, first I plug in 1. 1 to the 1 minus p is 1 times 1 over 1 minus p. So put that one first, like so. And then minus 1 over 1 minus p t to the 1 minus p. The question is, what happens to this piece as t approaches 0 from the right? In particular, it's going to depend on p, and we have a switch in the behavior when p equals 1. So take a moment to test a case where p is larger than 1 and a case where p is smaller than 1. I'm going to work through some examples over here on the left. So let's consider first an example where p is larger than 1. How about, just for a working example, let's try p equals 2. If we put in p equals 2, then we get t to the 1 minus 2, which is t to the negative 1. So that becomes 1 over t. As t approaches 0 from the right, this is 1 dividing by increasingly small numbers. This is going to blow up to infinity. So that's looking specifically at p equals to 2, but now you realize that if p is any number larger than 1, we would have t to a negative power. So t to the 1 minus something bigger than 1. And then if we have t to a negative power, we can invert it in this way. And then as t goes to 0, any such expression is going to blow up to infinity. So when p is greater than 1, we don't get convergence. This would diverge. On the other hand, let's see what happens if p is less than 1. The easiest number here to try would be 0. If p is 0, we're looking at t to the 1 minus 0. Whoops. I don't know why I wrote negative 1. Let me just fix that. Okay, t to the 1 minus 0, which is just t. As t goes to 0, this goes to 0. So that's convergence. That's going to give us an integral which exists. Then you say, okay, well, what would happen if p was anything less than 1? And you realize the same behavior would be observed. So if p is less than 1, this exponent on our t term would be positive, which means we wouldn't have this kind of inversion. So in particular, this limit would always go to 0 whenever p is less than 1. So when that happens, we can finish our computation. We get that this part is 0, and this part goes to 1 over 1 minus p. So we don't get convergence when p equals 1, and we don't get convergence when p is less than 1 in particular. When p is greater than 1, we get convergence when p is less than 1. If you compared this result to the similar computation that we did in Improper Integrals Part 1, the first video on this topic, you'll notice that it's similar, but essentially the opposite. What we said then was when we looked at a domain which went to infinity, so there we had improper integrals from 1 to infinity of 1 over x to the p, we got convergence if and only if p was greater than 1. Here we're saying we're not looking at the infinite domain case, we're looking at approaching that vertical asymptote at x equals 0. Instead, we need p to be less than 1. Notice the case where p equals 1 never gives convergence, so that diverges in both situations. And then greater than 1, less than 1, they essentially flip across the two types of improper integrals. Now let's talk about the situation where the function might experience something like a vertical asymptote in the middle of the domain of integration. So suppose that f is a function that we are analyzing from a to b, but it has a discontinuity at c, which could be, say, a vertical asymptote. What we want to do is take our computation and break it apart at c. So we will do the definite integral from a to c, and then from c to b, we'll treat these two pieces as separate integrals. For each, we use the techniques that we've already been looking at. So we will take c and replace it and take a limit. If both of these integrals converge, then overall the integral converges. If either diverges, then the original integral diverges. So consider this first example of this behavior. We are looking at y equals 1 over x from -1 to 1. 0 is actually not even in the domain of this function. So essentially, we're trying to integrate a function across a vertical asymptote. In order to try to do that, what we need to do is break it up so that this turns into the integral from -1 to 0 of 1 over x dx plus the integral from 0 to 1 of 1 over x dx. Now we can treat each of these as its own improper integral of the type that we've already seen. In fact, if we just look at the second one, we already know that this diverges because it's the situation that we were just looking at with p equal to 1. So I don't even need to take this any further. This also diverges, same situation, but just knowing that the second one diverges is enough to tell me that the original integral diverges. So this integral does not exist. Now let's consider the integral of x over x minus 3 from x equals 0 to x equals 5. You'll notice that the denominator has a problem when x equals 3. In particular, this function has a vertical asymptote. So that means that we shouldn't try to integrate from 0 to 5. We need to split this computation up at 3. So let me first just write the split. So we will say that this should be treated as the integral from 0 to 3 of x over x minus 3 dx plus the integral from 3 to 5 of x over x minus 3 dx. In this situation, I'm not yet going to take 3 and replace it with t and u or something like that. In fact, I might not even need to do that in this computation. Let's do a u substitution where we let u equal the denominator. So for both of them, set u equal to x minus 3 so that du is just dx. That means that the denominator will get replaced with u, and the numerator will get replaced with u plus 3. So this is that example of a u substitution where you end up kind of solving for something else in the integrand in terms of u. So in particular, u plus 3 will replace the numerator x. Okay, let's keep going, where if I need to, I'll bring in the limiting process, but let's see if we actually need that. Here, we are going to change our bounds. When x was 0, u is -3. Whereas when x was 3, u is 3 minus 3, which is 0. Then our numerator becomes u plus 3 all over u. Similarly, for the second integral, we'll go from 0 to 2. So x is 3 to 5 is like u is 0 to 2. U plus 3 over u. I'm going to go ahead and take this fraction. It's the same fraction, but I'm going to break it into 1 plus 3 over u du. Okay, take a look at that and see if you recognize the kind of behavior that we've been looking at. Both of these integrals are giving us an expression that looks like 1 over u to the 1. In other words, this expression here is the situation for 1 over u with p equal to 1. So we could think of just this part as the integral from 0 to 2 of 1 over u du. Maybe we'll throw a 3 in front. The upper bound is 2, but the upper bound was not what caused these situations to diverge when p equals 1. It was the behavior at 0. So this is going to diverge because it's of the form p equals 1. So overall, this integral diverges. So in these computations, if you recognize that those cases we looked at where you have expressions that look like 1 over x to the p for different types of p, if you recognize those pieces in your computation, you may be able to immediately assess whether or not your improper integral is going to converge or diverge without actually needing to pass to the limiting process. Now let's look at an example that might be a little bit more advanced. So we would like to integrate or assess 1 over sine of x from 0 to pi. Sine of 0 is 0. So I'm going to just start making some notes here about the sine function so that we can try to understand 1 over the sine function. So sine of 0 is 0. If I start looking at, say, the graph of, how about just the graph of sine? We're interested in the graph of sine from x equals 0 to x equals pi. We should know what that looks like. It has x-intercepts at integer multiples of pi. It comes up like this, oscillates to the left and right along the x-axis, but essentially looks like this from 0 to pi, where this part here is 1 at pi over 2. This is y equals sine of x, not y equals 1 over sine of x. What I would like to try to do is, instead of anti-differentiating this expression, I would like to try to compare 1 over sine of x to 1 over x. So this is my new goal. Compare what we have, 1 over sine of x, to something which we now understand very well, which is 1 over x. Okay, so I'm going to make some more remarks now about sine function. We know that the slope of the tangent line at the origin is 1. So notice d dx of sine of x when x equals 0. This is just my way of saying the derivative of the sine function at x equals 0 is cosine of x at 0, which is 1. So the tangent line to this function at the origin is the line y equals x. Whoops. Trying to draw a tangent and I sort of moved away. Okay. So we're right against y equals x. Let me clean this up for a second. I sketched this graph fairly accurately, which means that this part of the sine oscillation that I've pictured here does in fact stay under the graph of y equals x. But how you could see that is if you look at the second derivative of sine, okay, that's the first derivative of sine, which is cosine. So in other words, let me write cosine of x prime. That is negative sine of x, which is less than or equal to 0 from 0 to pi. That means that our function here is concave down. So from this point, we bend down, we're under our tangent line. So we know that y equals sine of x is concave down. And it's sitting under the tangent line that we have at the left point of this domain. This is just me trying to justify algebraically that this picture is correct. But if you were to just graph this, you could set up the comparison that we're going to make. So just trying to give you kind of on paper how you can work out that this is the correct way to relate the function y equals x and the function y equals sine of x. So now that we know that we're bending down under the tangent line, we can say that on the domain in question, sine of x is less than or equal to x. Those are the denominators of the two functions that I would like to compare. So if I take their reciprocals, the inequality flips. Neither would be defined when x is 0. So let me say on the interval from 0, not including 0 through pi, we know that 1 over sine of x is greater than or equal to 1 over x. Okay, so now I have a comparison between the integrand that we started with and an integrand 1 over x, which we've already analyzed. We know that on 0 to 1, and therefore on 0 to pi, this function, which is one of those functions where p equals 1, it encloses an infinite amount of area. So this from 0 to pi, this integral from 1 over x, it diverges. Since this is enclosing an infinite amount of area under its graph, and this is over that graph, this is a function which is higher, it's going to enclose, if anything, more area. It's not going to enclose less area. So if this does not exist because it's enclosing an infinite amount of area, then this one has the same property. So this diverges by comparison. So it's like this integrand is greater than or equal to something which is positive and diverging. Therefore, the area enclosed under the graph of this function from 0 to pi must be infinite. It's not a finite number. So this integral diverges.